Okay, microphone is working. Welcome back to day 3. Yesterday, we ended by discussing the definition of this possibly enormous Skein module. Right, this is a 4-manifold invariant, and you're allowed to put a link in the boundary. So as you'll recall, it's generated by all of these lasagna fillings, which are like some surface, but then they intersect some neighborhoods of these 4 balls, and in the boundary of those 4 balls you have links, and that's where you record the data of like the Kovanov homology or the Kovanov-Rosansky homology. So now the question for today is, how do you compute something that is of the form generated by like countably infinite many things modulo some local relations, right? And this is a very young area, and so we don't really have that many tools yet, but my goal for today is in the first 15 minutes to tell you about one of the tools that we do have that has been very fruitful. But before we go there, I just want to say a couple of things about where you could maybe take the field. So how do you compute this? Well, it's very natural when you think of a 4-manifold, or a smooth 4-manifold in particular, to say I'm going to break it down in terms of the Kirby diagram, in terms of handles. So you might ask, how does lasagna behave under handle additions? Okay, so the 0 handle, that's just B4, and it turns out the lasagna in B4 is just isomorphic to the original theory that you're working with. Let's count upwards. 1 handles. I'm going to say right now, it's hard. If you're interested, you should go to Choyu's talk next week in the conference portion of this workshop. But the reference right now is to maybe look at this paper by Anulescu, Walker, Radrich, where they talk about how to think about 1 handles. 2 handles, there is this cabled Kovanov homology formula. I call it a formula because if I take a diagram that consists of only 2 handles, I'm going to explain something where you take a colimit of some giant diagram. And at least this is something computable. Computable in the sense that if you're a human, you can try to compute it. It's a kind of an infinite process if you're a computer. But still, it's something where it relies on your ability to compute Kovanov homology of cables and things. So it's something that's a little bit more familiar. And this is the main reference for today. It's Manolescu Natalith, which we will talk about. And then there's 3 and 4 handles, which I will not say very much about because there's this proposition by the authors of this paper right here that says, if I, from W to W prime, these 4 manifolds, is the inclusion of a 4-manifold, smooth 4-manifold, W into W prime, then we have an inclusion map. And sorry, I'm going to go up here because I think you can't see very far down there. I star from this lasagna module. Right, so let's just think about no link in the boundary because we are interested in this case. Oh, sorry, you're looking at the seals background. I didn't set my computer to not to presentation mode, so there's going to be seals in the background. I'm sorry. Okay, so there's this inclusion map, and if this is an addition of a 3 handle. Then I star is a surjection. If you like very topological proofs, then I encourage you to actually go look in this paper or try to think about it yourself from the original definition of Skein lasagna modules. If it's by a 4-handle attachment, then I star is an isomorphism. So this is by basically thinking about just how many dimensions you have to wiggle around. Think about what the cocores of these handles are doing. So somehow 3 and 4 handles aren't so much of a concern. Having a formula for the 2 handles is very, very good. And then 1 handles is just kind of, at the moment, extremely difficult. Okay. But of course, many of the examples of exotic 4 manifolds will have both 1 and 2 handles in their Kirby diagram, so it'd be very helpful to have more technology toward computing that. Okay. So this 2-handle formula, oh, this is slightly moist. Okay. Oh, okay. All right, so the important theorem today is the following by Manolescu-Natalith. Let W be a 4-manifold obtained from B4 by attaching 2 handles to a framed link K. Let's say it has n components. Okay. Then remember yesterday I left as an exercise to think about how Skein lasagna modules decompose along an H2 grading. So if you have chosen a particular H2 class, this is going to be isomorphic to Zn, then we have an isomorphism between this ginormous Skein lasagna module and this thing that they define called cabled Kavanagh homology of this link. So cabled Kavanagh homology, it's still going to be defined in terms of KHR2. Okay, that's the notation for it. To the Skein lasagna module for GL2 homology, empty link in the boundary at the second homology class alpha. Okay, I spent all this time writing this down, but this is the important theorem today, but really to understand what it's actually doing, you have to understand what cabled Kavanagh homology is. Okay. Now, if you ever tried to write a paper where you describe cabling, there's going to be some notation involved. And I have about 5 or 7.5 minutes left. So what I'm going to do is first try to get the main idea into your head by looking at an example. And then I'm going to write down some stuff that maybe slightly doesn't really match with the example, but the point is that I'm going to be talking about the components of this construction in generality, like sort of from the Kavanagh-Rozansky setup for like GLN homology. But in the Kavanagh case, a lot of things simplify, and what you actually end up getting is something that basically is the content of this picture. So let me first just start with this picture, right? This is a Kirby diagram. It's a hop link, and luckily my framings are all 0 here if I want S2 cross S2. So I can actually draw cables, for example this one, of my framed link K. I'm going to choose a second homology class, and it's isomorphic to Z2, Z squared. And so I'm going to choose, let's say, 1, -2. So what I do is I'm going to build a directed system. So some diagram, it's going to be a two-dimensional directed system, where I first start at the top with a cabling of my framed link according to my homology class. So you should think I'm actually attaching these disks, or like, morally speaking, the H2 class is like you're attaching disks with like this orientation, negative orientations for this part of this component of the link. Now, that's number one, that's cabling. Number two of this construction is that I don't actually take the Kovanov-Rosansky homology of this link. I have to symmetrize, or I have to think about taking the components of the cabling, and there's an action by a braid group that basically passes the hoops through each other. Okay, so imagine you have two parallel hoops. There is a cobordism that kind of swaps them, right? You can go this way, you can go this way. That is the second part of this construction, which is the braiding action on each of the cables. Now, if you look really closely, I didn't actually write a braid group. I wrote symmetric groups acting on this. This is something special to the GL2 homology case. For Kovanov homology, Grigsby-Licata-Verley showed that the braid group action actually can't tell the difference between sigma I and sigma I inverse. It actually descends to a symmetric group action. Okay. You also might be concerned that at some point, say here, I am acting by S3 on strands that are oriented in different directions. That is a valid concern. Technically, I need to be acting by the braid group, the P part of the braid group that actually only swaps the parallel strands. So you separately permute the strands that have different orientations. But it's Manolescu and Natalis show that because of some other relations in the lasagna, the cabled Kovanov homology definition, for this GL2 homology, it's actually okay. The third thing I need to tell you about is how I actually build this directed system. And this is the dotted annulus map, which is the bundt cake pan with one raisin that I was telling you about on day 2, maybe, right? I was talking about a cobordism. So the idea is as you go down, let's say I'm going down this direction, I'm applying this dotted annulus map, which introduces two anti-parallel components. So if you look at this blue cabling of the left component of the hop link, I first started out with one counterclockwise circle, but then I added two oppositely oriented circles. And these are like the boundary of that annulus map that I have just constructed. Cabled Kovanov homology is the co-limit of this diagram. Homologies. Yeah, so these are induced maps on the homologies. All right, so if you wanted to try to make a computer compute this, you can see how, like, in some cases it wouldn't terminate necessarily. So that's also something that people can try to think about. So I was going to write more about this, but I think you have enough information, and if I write any more notation, it's not going to help you much. So now I'm just going to write down the formal definition of cabled Kovanov homology so that Mike can take over from here. Okay, so what did I say? Just kind of a cheat sheet. The first part of this was there was cabling, right? So if K is actually the components K1, not disjoint union, right? Linked union with Kn, you can have K minus, which is let's just write it as K. K minus is like a vector that keeps track of how many of each of these components are anti-parallel to the orientation of each of the components of the link. K plus keeps track of how many components of the cabling are parallel to the original orientations. Okay, this is result of cabling. So this is a extremely cabled link. Second part of the notation, there's the braid group. Action on cables. Okay, so if you have a braid in the part of the braid group that preserves the orientations of the strands, technically, right? Because it doesn't quite match with the actual Kovanov case. Let's see. For the ith component of this vector, this will act on the cabled link. Sorry, this sentence should really start there. I'm sorry, you should never start a sentence with math, but yes. The braid, this thing, acts on this by braiding the components with the same orientation. Okay, and the notation for this is you know what? I won't even write down the notation. There's not enough space. Okay, and then part 3, sorry that I will have to write it here, are these annulus maps. There's technically, in the original construction, 2 annulus maps. There's one for each number of dots that you can draw on the annulus. This one is the map that goes from, let's say, here to here, that does not have a dot on it. Okay, and then there's the one with 1 dot, which also goes from the same domain to the same target, but has a different quantum degree. 1 dot. Okay, and with this notation set, I can write down I guess it's a definition, so I'll write definition. So let alpha be some homology class in for your 2-handle body. W, Z. Okay, and here's something interesting. Like, you have to have a starting point. At the top of my diagram, I basically chose some number of disks that represents this homology class. Starting at, let's say, alpha, I plus is max of alpha I and 0. This is all very silly to write down in front of people, but I have no better way of saying this. But you basically want to choose like a pretty small starting point. You don't need excess anti-parallel cables. And also, I'm going to introduce the notation. Okay. Then the cabled Kovanov homology of this framed link K is going to take a big O plus of just the GL2 homologies of my cables R, oh, sorry. R is a vector in a length n vector in the natural numbers. So this is sort of counting, like this is a natural numbers squared diagram. So I'm saying that if I travel down, let's say this direction once and this direction once, that's like 1, 1, right? I'm trying to write down this two-dimensional co-limit here. To R minus alpha minus, R plus alpha plus. Okay, so I compute a whole bunch of Khovanov-Rosansky homologies. I have to actually do a quantum shift, and this is going to be very important in the topological applications that follow, which Mike is going to talk about. Negative 2R minus this size. And I'm going to mod out by some relations that use these. So the first one, where this is generated by, first of all, if this is my braid group action, notation that I didn't introduce over there, but if this braid acts on V, that's going to be identified with my original labeling V. Okay. So this is the sort of like symmetrizations. I'm basically saying I'm going to take the symmetric part, or project to the symmetric, symmetrize all of these cables. And then 2, if you have the coordinates on the annulus map without a dot applied to one of your labels, then that's going to be 0. And if you have a dot applied, or a dotted annulus map applied to one of your labels, that acts as identity. All right, so I'm not sure how much of this really will stick with you. If you can keep this idea in your head that it's a co-limit of some construction involving these 3 ingredients, that is my goal for you. Okay, so now it's time for a costume change.
Check 1, 2. Hi, everyone. I'm Mike. Where is the not wet eraser? Is it this? This was great. Thank you, Melissa. The big picture is gone. So, I mean, Melissa sort of already said this, but let me try to, impress upon you one more time. The definition of these lasagna invariants, as sort of presented yesterday, it's gigantic, it's huge, it's sort of, the definition allows you to sort of prove some nice formal properties, such as these handle attachment, like the 4-handle and 3-handle attachment formulas Melissa asked you to maybe think about or go read about. But like any sort of situation with a definition like this, the definition on its own is basically not computable. And so something like this, while the diagram that she had up there may also look quite huge and terrible, it at the very least reduces the computations to link diagrams for links in, the diagrams are pictures in R2, or in 2 disk. Okay? A link diagram is a combinatorial object. And so from here, in principle, combinatorics should be entirely able to take over. That's what I really want to sort of push during my time this week. And I want to illustrate that, first thing I want to sort of point out is a let me just say quickly, we're not really going to get into it today, but this formula that is written here, it's written for Kovanov-Rosansky homology. It is also true for the Lie version. So. Okay, and for those of you who feel very familiar with Lie homology and Kovanov homology, there was a question asked. Was this giant diagram a diagram in the chain complexes or homology groups? The answer is homology groups. Okay, we really don't have a good way of sort of saying this for chain complexes. Okay. Despite that fact, okay, when you have a formula like this that's true for Kovanov and Lie, at any finite stage of the diagram, the Lie homology is related to the Kovanov homology by spectral sequence. Okay, if you want sort of an exercise to sort of really kind of see how much you can sort of pull out of this, here's an exercise. For two-handle bodies, this is we only have this formula for two-handle bodies. Let me just say it this way. The rank in some fixed Q degree of, well, let's try to make our S's. So what is our notation right now? I'm going to run out of space. So the rank for the Kovanov Skein lasagna is bounded below by the associated graded in that Q degree of, well, the dimension of this for the Lie. Okay. So at each finite stage, this is true because of the spectral sequence. And this is not some kind of obvious thing. You really have to go in here and think about, okay, yes, it was a homology group, but on finite stages, that came from a chain complex. I can think about what chain elements we're doing. Okay, regardless, that's just a little sort of side thing. The main thing I want to be able to talk about is that I want to present a situation in which the complications of this formula, what are some of the complications? Well, it's huge. Okay, you have these braid group actions. You have to think about the annulus maps and things. Okay, I want to present a situation where a lot of the complications just disappear. Okay, what sort of thing would allow us to say, oh, I actually don't have to worry about the braid group action, or I don't have to worry about these maps? And the answer is, what I'd like to present to you is, under what conditions do these groups, regardless of any of this, under what conditions do these groups just vanish in any given biograding? Okay, so it's not a super exciting story. This is, today I want to show the case where we get no information. The case where the Skein lasagna module just vanishes.
Excuse me.
Yes.
In the Lie case, we know the canonical generators. So can you say something about the relation we get in this case?
Yes, but not till tomorrow. Okay, yeah, so tomorrow the goal is to talk about the Lie homology. And, and yes, indeed, the canonical generators are sort of exactly what we're going to be sort of picking out and relating to sort of canonical generators of the lasagna. But I want to save that for tomorrow. Okay. So So here is sort of the question. Under what conditions do these groups, so this is R minus alpha minus okay. So just for simplicity, I'm going to present the case where K was just a knot, so I don't have to try to think about. Oh, sorry, it's not these groups. It's shifts of these groups. That's very important. Okay, so well, here's, in my opinion, the sort of trick that, I want to present this completely combinatorially in terms of link diagrams. And to do that, I'm going to introduce a little bit of notation. Okay, so here's a new grading. Do I do the positive or the negative? Positive. M for mixed is sort of the sum of the quantum and homological grading. Okay, I have a bigraded theory. I can take some specific combination of those. I'm going to take this combination. And the reason for taking this combination, I mean, if you don't already know the answer of how this is going to go, perhaps it's easiest to see that when you have a situation like this, by the way, I'm going to drop the 2, KHR is KHR2, okay, is that when you under this grading, there are no grading shifts. There are no M grading shifts in this formula for what you do with the crossing. Okay, if you go back and look at what the various grading shifts are in this formula, when you sum the gradings, there are none. Okay. Also, I guess I should write it. Melissa sort of mentioned there's sort of this isomorphism with the original Kavanagh homology, and I'm sort of using this to ignore I think, Melissa did not spend too much time talking about it. I don't want to spend too much time talking about it. The strict definition of these Kavanagh-Brzezinski things, one of these guys, depending on the orientation, should have like a thick edge, okay? But the isomorphism with the usual Kavanagh homology, I mean, there's something a little bit extra here to say, but essentially allows me to sort of ignore that. Or if you prefer, I'm sort of using that isomorphism to draw Kavanagh homology, or Kavanagh chain complexes for these things. Okay, it doesn't really matter for what we're going to do because we're really just interested in when groups are 0, and the difference between KHR and KH is sort of irrelevant in that scenario. All right, so what else? Do I need any other notation? Oh, well, no, but I should point out that, so there's no grading shifts in here, but this is still a framed invariant, and I want to track the grading shifts from framing. So which one's which? This one gives me a positive shift, and this one gives me a negative shift. Okay? There. There's like a one-liner. Okay. time. Okay. So let's talk a little bit about this sort of cabling situation. So if given your two-handle body is a two handles being attached to some knot with some framing. Okay, so first I just want to say, let's say I have a knot diagram for my knot. Okay, that's going to be the K. And then this guy, what's the diagram here? Well, I want to draw it this way. I'll explain in a moment. Okay, this diagram is just me explaining how to draw a diagram for cabling a knot when framing is involved. Okay, so this just means n parallel copies of K. Okay, like blackboard parallel, blackboard framed copies of K. All right, n being the total number of strands, and then I have to add in some framing twists. Okay, so F is a full twist. Well, okay, how many framing twists do I add? It's the framing minus the rise, so should I write that K here is the framing of my attachment minus the rise of the diagram. Okay, and what are these full twists? Like, what diagrams do I actually have to draw here? Well, I draw F for full twist, this little twiddle, because, like, I really mean a framed full twist, so things like this. Full twist on 2 strands. Full twist on 3 strands. Can I do this quickly? That's the diagram. Those are the sorts of diagrams that go there. The exponent is just that many full twists on top of each other. Okay, in particular, sorry. Etc. And then I'm going to let the non-twiddled version, well, let me write it this way. I have this sort of framing shift for individual strands. Okay, so F without the twiddle just means I've gotten rid of the kinks. Okay. Yeah. I'm not sure I understand the question. Can you say it again?
So I would say that putting this is not exactly the same what Melissa was preparing us with this annulars.
Oh no, this twist is not appearing because of the annulus. This is just this is to be viewed as one cable. This is just a picture of what it looks like when you cable a framed knot. Okay, and then there would be a map from this to the n+2 case. And that map would be an annulus that, well, it starts by sort of birthing a circle, and then it sends the circle through the knot, brings it over here, twists it around. K is just a framing number. That's all. That's all. Okay, so a whole bunch of combinatorics is what's really all that's about to happen now. So let's just point out what it is that we are interested in. And maybe this also, clarifies maybe some of that confusion as well. So we're interested in the homology groups for is it, I think, did I erase it? Yeah. Well, the homology groups we wanted were homologies of these cables. Okay? But they included this shift by negative alpha minus 2r, right, which is n. Okay? That was a quantum shift, which translated as a mixed shift as well, no homological shift. Okay, so there's a shift of negative n, and I'm going to also bake in this negative nk into the shift as well. So I can say that I'm interested in these diagrams. And r going to infinity is the same as n going to infinity if I have fixed alpha. Okay. So now, speaking of Lev-Rosansky, here's a procedure, as I'm aware, essentially due to Lev, for taking these full twists and simplifying them. Okay, so here's I'm going to outline a procedure and maybe leave the details as an exercise. Okay, again, it's just playing with pictures and combinatorics. Here's F2, okay, but I know that a crossing in this Kovanov-Rosansky world, if I'm just doing the mixed grading, I don't worry about grading shifts or anything. I know that a crossing really just sort of looks like there, I've sort of messed with the first crossing there. Okay, but I also know in the Kovanov-Rosansky world, one of these gives me an M shift. And then this one, I guess I'll write it, but it's not necessary. Okay. There's a simplification for F2, where normally this would be some kind of square, right? Some two-dimensional cube. Okay, actually I can just draw it as 3 terms. It's not that exciting for F2. Okay. Okay. F3 is the same thing as one strand doing this and F2. Okay, but I've already simplified F2. So this is the same as fair? Okay. I guess I didn't write it because there's nothing to write down. Radermeister 2 moves do not incur any shift at all. Or it is a framed link invariant, these things. There's no shifts involved in isotopies that don't affect framing. So this might as well be this. By the way, I keep writing like these sort of symbols. You know, these are some kind of complicated chain homotopy equivalences. Okay. All right. Okay, this one has another F2 in it right here. Okay, so another M is going to appear. Okay, and soon after this, we'll be able to say the right thing. So this guy is M. You got to sort of think about it for a moment, but okay, so what I want to point out about something is, okay, there's yet another M that can appear here. Okay, I'm not going to keep writing more. The important thing about F3 that I want to point out is that these M shifts, well, okay, let me write it this way. You know, this one is going to give a term that looks like the identity braid without an M shift. Okay, and then there's going to be some other terms, okay, that have M shifts either 0 or 1. Either 0 or 1. Some of them have 0, some of them have 1, of diagrams that are not the identity. Okay. Right. Again, okay. I have to do one more, and then we'll be able to like say something. So decide how much you want to write of this, but okay, okay, sorry. I should explain this notation. I've just basically said what the terms look like. I haven't bothered with the differentials, because in the end, I'm just going to be worried about when things are 0. I don't care about the differentials. Okay? So this guy, the groups for this guy, well, there's some kind of giant, well, okay, there's this one, and then there's plus either 0 or 1 shifted copies of things like this. Right? There's various diagrams like this. Okay? And now you say, okay, all these diagrams, if they're not the identity, then they all have some sort of turnback which can be pulled through. Okay? So this part, or maybe I should say this part, is the same thing as, okay, let me write it this way. There's sort of an upper half of delta, and there's a lower half of delta. And that one strand is still going through. But there's 3 strands out here, and there's 3 strands out here. That wasn't so helpful. This is the same as this. Right? Again, it's just pictures and combinatorics. But guess what? Here's another F2. And F2 can create another M. But if F2 creates another M, it creates another M by adding another turnback. Here is the general statement that you can sort of try to decide how to prove. Oh, I haven't simplified this one, but this one, there is an F2, and it can create an M. Let me not say so much, okay? Let me write the general statement. Sorry, are we out of time? We're out of time. Okay. I was thinking we had till 10:30, but that's not true. Okay. The general statement, let me write it down, and then next time we'll start by finishing the vanishing thing. And then we'll talk about Lee. So the general statement that I'm interested in here, exercise, induct to conclude that the full twist is a bunch of diagrams of the form these M shifts are actually counting how many turnbacks there are. Okay? I write this as like, there are some diagrams with, let's say, 23 turnbacks, but the M shift was 0. But the shifts are always between 0 and the number of turnbacks. Okay? I claim that next time it's going to be pretty easy to go from here and say something about when the things vanish. Okay, I apologize for going over time. Thanks, guys. So maybe this is the easiest way to say it. If you have two strands, I just have to tell you what the generators of the braid group do, right? A transposition takes maybe I should color them. Can I color them? Here's a Reitermeister 2 move. Okay. So let's see. I mean, it's another Reitermeister 2 move. I don't know how clear this is. It does this. It permutes them in sort of the way that makes the most sense. I don't know. And this doesn't care. This process, I drew it for the unknot, of course, right? But any knot will do. Any framing also can get handled this way. This is, quote unquote, all that you're doing. Okay. But as maybe you can imagine, it's complicated to keep track of when you have a lot of them. But you're symmetrizing with respect to this idea.